All right, welcome to today's lecture where we're going to be covering Newton's third law of motion. So up until this point, we've talked about the first law where the net force is equal to 0, and therefore our object can't change its state of motion, whether that's going to be at rest or moving in a straight line at a constant velocity. We also discussed the second law of motion, which states that an object has a net force acting on it, and therefore it is going to accelerate. So net force is equal to mass times acceleration. And last time we spent a little bit more details looking into some of the forces. So we looked at, in particular, the force due to gravity, which is, we have it as Fg. It's going to be equal to the mass of the object times the acceleration due to gravity. Where m here is the mass, it is a property of the object. It doesn't change based on where the object is located. And we very briefly talked about weight. We said, hey, weight's a force. It is not the force due to gravity. There is something different about it because we also need to take into consideration any other accelerations we have in our traditional y direction. So, weight is a force, but it is, in reality, it is how we perceive how big our mass is. It is not a force by itself in all what's said and done. Weight is a force that considers other things. We also talked about friction. So for static friction, it has a range of values, but we're primarily going to be interested in the maximum value for this friction. So it's going to be the coefficient of static friction times the normal force. Well, it's pretty similar to the kinetic friction, which is a constant value. It's just the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. And we saw how we can use these for some free body diagrams and some problem solving within Newton's first and second law. So today what we're going to be doing is we're going to be introducing rotating our coordinate system. So that's going to be done in this first video. The second video is going to talk about interacting objects, analyzing interacting objects, and then Newton's third law. So that's just going to kind of be building up to Newton's third law and then its actual statement. The third video, we're going to talk about ropes and pulleys. So getting a little bit more into tension and how we're going to be utilizing tension in this class. Technically, we're covering 7.5 today. That section is just examples. So that is for you to go through and look at. I'm going to be doing examples in the third, and then there's going to be a fourth bonus video that's an example. But that is me covering, quote, quote, that particular section. So let's talk about rotating our coordinate systems. So far, we haven't really been focusing on motion in two dimensions. We've been doing one dimension and then the other. So we want to think about what's going to happen moving in two dimensions. So here we have a very classic example of a box on an incline. And we can go through and we can draw the forces on here and figure out what's happening. So let's use the standard coordinate system in this case. So that means that when we're drawing our forces, we're going to have y up positive and to the right positive x. So we need to draw our forces onto here. So we're going to have our normal force being perpendicular to our surface. That's just the definition of the normal force. We know that gravity points straight down. So we have Fg. And let's say for the sake of making this a more interesting situation, let's say we have friction and it's pointing up the incline. We'll have kinetic friction because our box is going to slide down the incline. So when we go through and set up our forces, in this particular case, we are going to need to know information about our angle. Because when we go through and set these up, we need to break our forces into components. So if we look at the x direction, for example, we're going to start at the top, so at the positive y, and we're going to work towards positive x. There's some component of the normal force in the x direction. I'm going to work my way down. Gravity is purely in y, so I don't need to worry about that. There's some amount of friction in the x direction, and I am moving in the x direction. So I'm going to have a component of the normal force and a component of friction related to mass times acceleration. That doesn't seem too bad. I can solve for the normal force. I can solve for the components if I spend some time doing some triangles. Let's hold off on doing that. I need to look at the y direction. Well, if I have a component of a force in x, I also have it in y. So normal force points upward, so it's positive. My force due to gravity is negative, it points downwards. My force due to friction in the y direction is positive, and I'm going to accelerate in the y direction. Now, looking at this, I have a problem. Friction is making this a lot harder of a problem, but I have one here. I do not know the acceleration in x or y. I probably don't have these values given to me. It's probably what I'm solving for in this question. In order to find, oh sorry, that shouldn't be s, that should be k. So in order to find the coefficient, or I have the coefficients of friction, let's assume, in order to solve for the normal force, how am I going to solve for the normal force? I don't know the normal force, and because I don't know the normal force, I can't find the frictional force. So I in reality here have three unknowns, because if I can solve for the normal force in x, I can solve for it in y, and that's going to allow me to solve for my friction. So I don't know my normal force, I don't know the acceleration in x, and I don't know the acceleration in y. So I have three unknowns and only two equations. This is mathematically not solvable. I cannot solve this as it is. If I had one more piece of information, I could solve it, but based on just having these three forces, I have three unknowns, I can't solve it. So we want a way to be able to go through and solve this. And what it's going to have to do is change our coordinate system. So in the previous example, we had acceleration in x and y. We had Newton's second law being applied twice. But what if I can change my coordinate system so in one direction I have Newton's first law, and in the other direction I have the second law? Well, my normal force still points up, gravity still points down, and friction still is going to point up this incline because my box is moving down the incline. So if I could find a way to solve for my normal force, that's going to make it so that things are a lot simpler for solving. So I need to think about, how is my box moving down the incline? My box is where it currently is, and a couple seconds of later, or however much time later, it's going to be here. Right? It's moving down on the surface of the incline. So what I can pretend is that my object is moving in one direction, the direction of the incline. So with that, if I say my x direction points down the incline, that means that my motion is only in one direction. I'm only moving in x. Because my y direction needs to be perpendicular, I'm not moving in my y direction anymore. I'm only moving in my x direction. Because x is parallel to my surface. So that means that now, when I go through and I write the sum of my forces in x, I'm going to have a component of my force due to gravity in x. But all of my kinetic friction is now in the x direction. All of my normal force is now in the y direction. So I'd have normal force minus force due to gravity in y. And because I'm only moving down the incline, and my y direction is now perpendicular to the incline, I'm not moving in y. But I am moving in x. And in fact, that's the only direction I'm moving in. So now I can solve for my normal force. Now that I've solved for my normal force, I can now find a numerical value for my kinetic friction force. I can solve for my acceleration value. Here, this is solvable. So I can solve this. So I want to talk about this force due to gravity and finding the angles. So let's do that now. Oops. So basically, by changing our coordinate system, we're only moving in one direction. So we have the first law in one direction, the second law in the other. So now let's look at changing the force due to gravity. So here we have our unit circle. Now traditionally, again, y is going to be upwards and x is going to be to the right. So the goal of tilting our coordinate systems for an object on an incline is to make it so that our x direction is parallel to the incline. So let's say hypothetically, our incline, let's just make it down here. It's a 45-degree incline. So that means that I want this to be my new x direction. Realize I probably should have picked a unit circle without some letters on it. But this way we can see value-wise how stuff shifts, and I also like the guiding lines for myself. So I've moved downward 45 degrees. X and Y must be perpendicular to each other. So that means that my Y direction also needs to shift 45 degrees in the same direction. So that's going to put my Y direction here. So I've shifted my right angle the same amount. In this case, I've done 45 degrees, but in reality, my theta value should be the same as my incline. Now, we're not going to be limited to just changing our axis for an incline slope. What we'll see in the examples that I do at the end, I change it for something that's falling straight downwards. And I'll talk about why that's the case when I get to those. But here, we just want to make our life as simple as possible by only moving in one direction. So we're shifting our entire coordinate system. So let's look at gravity in particular. Gravity points straight down. This is the force due to gravity. In our traditional coordinate system, it's in negative y. Right? So we could draw our normal coordinate system in here. Let's do straight lines. X, y. We're going to shift it some value theta, whatever that incline happens to be. So this is our new y value and our new x value. So when we go to break our force due to gravity into components now, the way we can think about it is we take our new y-axis, and we draw the negative y-axis. So this is now negative y. And with x, I can draw, I technically can change where my origin is, right? Or I can think about this as completing my triangle. This is the x component of my triangle that I've made. So I have a y component and I have an x component. The amount I've shifted from traditional negative y, which is in the same direction as the force due to gravity, and new negative y is theta. So if I look at my triangle, my force due to gravity is still in the same direction. But my force due to gravity in y and my force due to gravity in x are making a triangle, a right triangle. However, if we look at it, the force due to gravity in y is going to be Fg, but if I look at my triangle, it's adjacent to my theta value. So I'm going to have Fg cosine theta, and this is the y component of my force due to gravity with this type of coordinate system tilt by trying to make my motion move in x. I can do the same for the x direction. I'm going to have the force due to gravity. Here, the force due to gravity in the x direction is opposite my angle. So I'm going to have sine theta. So when we are breaking forces down into components, if we're just taking the coordinate system and tilting it, in this case I've tilted it to the right, or you take the same original coordinate system, you can equally tilt it to the left. There's nothing wrong with that. You can instead say, well, I want my coordinate system to be y up here, and then x has to move the same distance as well. So we can go either direction as long as it's the same amount for x and y. We just need to make sure, and when you are beginning this, going through and drawing a picture similar to this will be beneficial because you can see, based on the coordinate system you have chosen, if y or x are opposite or adjacent. If you're just taking x and y from standard and tilting it a little bit, y will be cosine, x will be sine. If you are changing it 90 degrees or more, that's going to be a different situation. All right, so that's going to wrap it up. We're not going to do an example for this right now because most of the examples that have coordinate system shifts require Newton's third law of motion in this textbook. So we're going to wait until doing some examples of tilting the coordinate systems until that time.